Hi everyone, so we're going to solve some inequalities here. We're going to use the technique of graphing to do this. So I just want to start off by saying maybe one of the things that we need to think about here is actually graphing 5 over 2x minus 1, but then it is also equal to 3. So in this instance what we'll do is we'll be graphing one equation and equaling it to a value, and then what we'll do is we know that it cannot equal that value because the inequality says when is it less than that value. So let's do this one first. So I'm going to graph the following. Okay, so we're going to go over to here and we're going to go to a graphing screen, and I'm going to bring up the fraction key, and I'm going to graph 5 over 2x minus 1 first. Okay, now I'm going to graph 3. Okay, so like I said, we don't actually want to know when the graph is equal to 3, but we want to know when the graph is less than 3. Right, so if we think about that, we want to know, so at this point here where the crosshair is, that point is when the graph is equal to 3, and it only equals 3 at this point. See, the graph does not intersect anywhere else. So what we can do is we can find the point of intersection. Right, this will be helpful. Okay, so it's at 1.33. So when x is 1.33, the graph is equal to 3. So this value of this function is equal to 3. Now we wanted to know when the function, this thing here, when the graph, the blue graph, is less than 3. So if we go over to here, we can see that the blue function, the graph, is lower than the red line here. Right? So that means then for values greater than 1.33, the graph will be lower than 3, right? So we can go ahead and do that now. So we want to, one of our solutions, which I'll write in green here, is if x is greater than 1.33, okay, this statement is true. Now, that is not the only solution there, though. If we go back and we have a look, we realize that anything here to the left, the graph is actually higher than the red line, right? So the expression less than 3 does not make any sense, because no, the graph is greater than 3 here. But there is a special point here on the axes where we can see there is like an invisible line known as the asymptote, which the graph does not exist. Now, if you want to know where that is, it is what value of x makes the denominator equal to 0. So 2x minus 1 equals 0, therefore 2x is equal to 1, therefore x is equal to a half. Now, if you didn't know that, well, you can always bring up the table function. So menu, table, split screen table, and we're just looking for where the graph is undefined. Now, it's not so obvious because this table goes only up in integers. So that does cause us a problem that we can't easily see where the graph is undefined if it is not an integer. So I'm just going to remove the table there. Menu, table, remove table. So I'm just going to go back to this idea about we need to figure out when the denominator of this graph here is equal to 0. So if we go back over, we'll do some quick calculation in the notes here. When is the denominator? So when is the 2x minus 1 equal to 0? Or 2x is equal to 1, so x is equal to a half, as I said. So that means when we have our graph here, okay, when, oh, I apologize, yeah, sorry, let's just go back here. So I can't draw on here, but here at half there is an asymptote, okay, and I can't quite draw on the graph here, but I can tell you now that there is an asymptote here at a half. Okay, so if we go back over to the sketch, if I drew a yellow line here, that means that this value here, x is equal to a half, and then we have our function, our graph, which is basically doing this. So that means that anything to the left of this function, we notice that the graph is now lower than 3. So remember, we have a line crossing at 3, but this whole part of the graph is below that line. So that means we have another inequality that we have to state that x has to be less than a half, and this will be true. Okay, so if we go back over to the graph here, try and do it, we have this asymptote occurring at a half, and if we go to the left of that asymptote, so imagine there is an invisible line here, to the left we can see that the graph is below 3, below 3, below 3. Okay, so a little bit of a tricky question, but we got there. Okay, we're going to look at 1.5, but this time part B. So again, it's another inequality. When is the graph less than or equal to 0? So we're going to go over to our graphing page here, and we are going to graph 6 minus x squared. No, sorry, 6 minus 3x minus x squared. Okay, and the question states, when is the function, if we look here, when is it less than or equal to 0? So if we go over to the graph here, let's figure out when it's equal to 0, which is here and here. Remember, you're equating it to like when is it equal to 0 on the y-axis. So here this is equal to 0, and here it is equal to 0. It's what values do you substitute in this to make 0? And remember, this is the y value, right? So menu, analyze graph, zeros, and we're going to figure out the zeros. There's 1, menu, analyze graph, zeros. Okay, so we've got the values of this equal to 0, but the question, remember, states when is the function less than 0? So that means the function is lower than 0 if we are to the left of this point and to the right of this point. Anywhere in between these 2 points, the function is greater than 0 because it goes all the way up to, well, past 6, right, because it's off the screen. So we don't want anywhere between these 2 points. So we have 2 inequalities. One is that x needs to be less than negative 4.37. So x needs to be less than, oh, by the way, it says less than or equal to, because it says it here, less than negative 4.37. and greater than or equal to 1.37. So x is greater than or equal to 1.37. That is the end.